11.6, absolute convergence and the ratio and root test. So here we're going to be given a series, the summation of a sub n, where we're going to consider all of our entries of our sequence as absolute values of the terms. So if this is the way our series is set up, we can call our series, the summation of a sub n, is called absolutely convergent if the series of the absolute values in E, the summation of absolute value of a sub n, is convergent. If our series has only positive terms, then the absolute value of our sequence function is equal to the original sequence function. So absolute for convergence is the same as convergence in this case. Definition of 2, a series, the summation of a sub n, is called conditionally convergent if it is convergent but not absolutely convergent. We'll look at an example of that. Okay, example 1, leave yourself some extra space because I'm going to sneak another problem in here at the bottom. So here is our series. Normally we would see the -1 raised to the n minus 1 power, and let's use the alternating series test. So condition number 1, we take the limit of 1 over n squared. Remember, we get rid of the negative signs. And that's going to approach 0, so that's satisfied. Then we got to prove that it's decreasing, which we put in n plus 1 in for the location of n. We'll set it less than or equal to 1 over n squared. We cross multiply. Again, remember that the denominator crosses up to the numerator and stays there, not the other way around. So n squared is less than n plus 1, that binomial squared, and that's easy to see that that's true. So since both statements are true, we can say our series converges by the alternating series test. Is it absolutely convergent? Now we put absolute value bars around the entire function. We don't just remove the -1 raised to the power as we did in the alternating series test. So that's our summation of 1 over n squared, and that's a p-series, and p is equal to 2, which is greater than 1, and it converges. So therefore, our series is absolutely convergent. All right, I want to sneak another one in here because not all the time will you be able to see your -1 in the problem. So if we consider the series a summation of cosine of n over n squared, if we start looking at putting in 1 in for all of our n's and starting to plot those, you can see down below here that we get 1 positive, 3 negatives, 3 positives, so that it doesn't alternate back and forth. So here's a good case. Since we don't have alternating signs, we really have to put the absolute value bars around everything. But then again, the absolute value of n squared is still n squared, so our absolute value bars move up to our cosine of n. Well, we know that cosine, its range is from -1 to 1, and if we're taking the absolute value of cosine of n, that means these answers will always be less than or equal to 1. So therefore, if we divide n squared into both sides of our inequality, then our absolute sequence is less than or equal to 1 over n squared, which we just had up here. So by, again, the direct comparison test, we can show that it compares to this sequence, which it converged up above, and therefore we can say that this sequence that we are dealt with is going to converge by the direct comparison test, and it converges absolutely as well. Example 2. Now we have -1 to the n minus 1 power over n. We know that this is an alternating harmonic series which converged. We proved that with our alternating series test once before. So that's a preview of what we did before. Same thing. The limit as n approaches infinity of 1 over n goes to 0. We put n plus 1 in for n, see if that's less than or equal to 1 over n, cross multiply, yes it is. So we know it converges by the alternating series test. But is it going to be converging absolutely? Put absolute value bars, becomes 1 over n, and we know that, hey, that's a p-series or a harmonic series. P is equal to 1, less than or equal to 1. This diverges. So since our series is convergent by the alternating series test, however, it is not absolutely convergent. So therefore, we're going to call this series conditionally convergent. Okay? So Theorem 3 says if a series is absolutely convergent, then it is convergent. So this tells us that, hey, you know what? We should probably test for absolute convergence first. And therefore, if that's true, then we know it's also going to be convergent. So what I suggest is a flow chart. What we should do is we should always check for absolute convergence first. Because if that converges absolutely, then it implies convergence. That's what theorem 3 up here says. If it's not convergent, like we saw in the previous example, then we want to try the alternating series test. So we test our two conditions. If one works, we continue. If one fails, then that's our divergence test. Then we stop right there and we know it's divergent. Continue to 2. If it is going to be decreasing, then yes, it is conditionally convergent. If number 2 is no, then there's no conclusion. We have nothing we can do. So this is a flow chart that you should consider using. Always test for absolute convergence first, because once you have this, you're done. If it converges absolutely, then it will also converge. All right, given our series. Oh, wait a minute. This is a typo error in your notes. Please change the sequence formula. Thank you. Get this changed out. All right, so by our flow chart, we're going to test to see if this is absolutely convergent. So absolute value bars around the whole thing. We're going to have to do a comparison test. This is gone. We have n over n squared plus 4, which we can compare it to n over n squared, which is 1 over n, which is our harmonic series that diverges. Okay, so we're going to compare it. Now we're going to do the limit test with this. So we're going to show that the limit of our original function, n over n squared plus 4, and over our, what we're similar to, 1 over n, and see if we get a constant value that's finite. So n over n squared plus 4 divided by 1 over n, what we compared it to. We don't divide by fractions, we multiply by the reciprocal, so multiplying the n to the top up here gives me n squared. And we can see this is your horizontal asymptote rule. Top power, same as bottom power, leading coefficient ratio, 1 over 1. Your limit is 1. Well, therefore this diverges. Our limit was equal to c, which is finite, so it does verify that, step 1, that it diverges. So this is not absolute convergence. So here's our flow chart. It failed, so now we got to go over and try the alternating series test. Our limit n over n squared plus 4 goes to 0. We can see that the bottom's getting bigger faster than the top. Are we decreasing? This could be a problem here. You'd have to FOIL this out. You're going to have big polynomials, ugly things, could be more difficult. Suggest we just call it a function f of x and do the first derivative test. So if we do the quotient rule, here's our x squared plus 4 squared on the bottom, x squared plus 4 times the derivative of the top, which is just 1, minus the top x times the derivative of the bottom, which is 2x. So this gives me minus 2x squared. Add it to the x squared, gives me 4 minus x squared. Now we take the 4 minus x squared and make sure that it's less than 0, solving it for x. We get x has to be bigger than 2. Once you're bigger than 2, then this sequence begins to decrease. So both statements are true and converges by the alternating series test. So this series does converge, but it's a conditional convergent, not an absolute. All right, so we got to be able to state the difference between the two. All right, come back in a second for part 2.